JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, ROPA. So in today's lecture, we'll be exploring the key fundamental concept of the chemical reaction engineering, which is the general mole balance equation. Right? The general mole balance equation is a backbone to design any reactor system. Okay, the general mole balance equations will help us to track how the change of moles of any chemical species takes place inside any chemical reactor system, right? Whether it may be batch reactor, yeah, plug flow reactor, continuous stir tank reactor, semi batch reactor, fluidized bed reactor, semi batch reactors, or we have the bioreactors, right? So any different types of reactor, by understanding the general mole balance equation, we can analyze, we can understand how the chemical species, the moles of the chemical species will change inside the reactor systems. Okay, so the general mole balance equation, which will also account for the input term, output term, the generation term, and the accumulation term, right? So by understanding the general mole balance equation, so in today's lecture, by understanding all the key concept of chemical reaction engineering, which is the general mole balance equation, so by end of this lecture you will understand not just an equation but its meaning, and we'll also understand how we can apply to the designing of any reactor system, right? And we can answer to all the questions. Okay, so let's say the first question which arises is, why do we study the general mole balance equation? Okay, the general mole balance equation is the backbone of designing any reactors, right? In order to design a reactor, we need to know like how many number of reactants are feeding to the reactor system, right? How many number of reactant moles are feeding to the reactor system. So let's say here we have the reactor system. So here the figure indicates the reactor, right? We have the reactor and we have the stirrer, okay, which is used for the mixing, for the uniformly mixing of the reaction volume. Okay, so in order to design a reactor, we need to understand, like we need to know how many number of moles of reactants are feeding to the reactor system. Okay, now the reactants are present in the reaction volume. This is the reaction volume, right? This is the reaction volume. So in the reaction volume, in the reaction environment, the reactants will get interact with each other, and they will react. And after the completion of the reaction, we will get the products, right? Then after the completion of the reaction, how many moles of products are exiting the reactor system? Okay, so by understanding the general mole balance equation, we can also understand the, if let's say if we have the accumulation, let's say if we have the unreacted reactants, which means reactants those doesn't take part in the reaction, are the unreacted, which is not reacted and which is not get converted into the products, are called the unreacted reactants, right? So let's say if we have the unreacted reactants accumulated inside the reactor volume, right? Unreacted reactants which has been accumulated inside the reactor volume, or let's say any reactant or product species may accumulate inside the reactor volume. Okay, so by understanding the general mole balance equation, we can understand the input term, which is the feeding to the reactor part, reactants which are feeding to the reactor, it's called the input term. The output term is the product. After the completion of the reactor, the moles of product which is exiting the reactor, right? After completion of the reaction, the moles of product which is exiting the reactor system is called the output term. And let's say during the run of the reaction, the some new products, the reactants will get consumed and new products will get generated, right? It's called the generation term. Okay, and accumulation term is the unreacted reactants or product or reactants which is accumulated inside the reactant inside the reaction environment in the reactor system. It's called the accumulation term. So by understanding the general mole balance equation, we will be able to answer all the questions, right? The second is the connection between the chemistry and engineering. So in the chemistry, in chemistry we'll understand the rate equation, right? Rate equation we can understand. Let's say the A reactants will get converted into B, means A gives B, right? Or let's say we have two reactants, A and B, reacting with each other, right? So let's say we have two reactants, A and B, reacting with each other, and after completion of, with the progress of time, after completion of the reaction, the A and B will get converted into new products C and D, right? So in chemistry, we will understand the reaction equation, also termed as the rate equation, okay? But as an engineering perspective, as a chemical engineer, we need to understand the engineering perspective, which means the rate of the reaction, which means the reaction speed. What I'm trying to say, let me be very simplified. The reaction speed means the rate of the reaction, the rate of the disappearance, and the rate of the formation. The rate of the disappearance of the reactants during the progress of the reaction, the rate of the reactants of the disappearance means the reactants will get disappear, the reactants will get consumed and will converted into the product, right? So how fast the reactants are getting consumed during the run of the reaction, and how fast the products are getting generated during the run of the reaction inside the reaction environment, okay? So it's the reaction speed. So as a chemical engineer, we can understand the reaction speed of the reactions and the products, right? Second, the change in concentration with respect to time and the position in any different reactor system, right? So how the concentration will change with respect to time and with respect to the position inside the different types of reactors. Let's say reactor volume, okay? So let's say if we are designing the reactor system, right? So we need to design such a type of reactor and with specific volume, right? Which we, by using the specific volume of the reactor, we will be able to achieve the desired conversion, selectivity, and yield of the desired product, right? So by understanding the general mole balance equation, we will be able to answer to all the questions, okay? And let's say if we are using the catalyst in our reactions, let's say we are having the catalytic reaction, then what amount of volume of catalyst we will be utilizing for our catalytic reactions, right? So by understanding the general mole balance equation, we will be able to answer all the questions, okay? Now we can also compare the microscopic reactor performance with the macroscopic reactor performance, which means the microscopic reactor performance is the behavior inside the reactor, right? So the microscopic reactor performance, which means behavior inside the reactor volume. So this is our reactor volume, right? So let me be very simplified. The behavior inside the reactor volume, which means at the very tiny level, right? At very tiny level, at the molecular level or the kinetic levels, right? It's called the microscopic reactor performance, right? So here in microscopic reactor performance, we have the main quantity as reaction rate, right? The rate of the reaction can be defined as the change in number of moles of any species I with respect to the time and with respect to the unit volume, okay? I already explained. So if you want to recall, I request you to please watch my previous lectures, okay? So where I explain the rate of the reaction, how we will define the rate of the reaction, followed by in the second lecture we understand the rate of disappearance and rate of formation, right? So if you want to recall, I request you to please watch my previous lectures. So in the microscopic reactor performance, we'll understand the main quantity is the rate of the reaction, right? So microscopic performance depends on the local variables, which means the rate of the reaction is the function of concentration of species, right? The rate of the reaction is a function of concentration of species, temperature, pressure, catalytic activity, diffusion and transport rate, which means The rate of the reaction is the rate of the reaction depends upon the concentration of species, the temperature, pressure, catalytic activity, and diffusion and transport rates. So in all these variables, the rate of the reaction will depend. Okay. So in order to understand the microscopic reactor performance, we have the two factors. The first one is the intrinsic factor, and second is the extrinsic or transport factors. Okay. So intrinsic factor, which means at a very microscopic or molecular level or the kinetic level, right? So intrinsic factor at which we analyze, we understand at the molecular or kinetic level, it's called the intrinsic factor. So in intrinsic factor, we have concentration of species. Let's say if we have the higher concentration of molecules, so let's say if we have the higher concentration of reactants, okay, then what will happen? We have the higher molecules of reactants. So if we are having the higher molecules of reactants, so those molecules will collide with each other, and due to which the rate of the reaction will increase. The reaction between the molecules, the reactants will increase, due to which the rate of the reaction will increase, right? It's called the intrinsic property. Okay, intrinsic factor. Second, the intrinsic factor, in which we also have the temperature, which means if we are having the higher temperatures, at which the molecules or the reactants will have the higher rate of reactions, right? At higher temperatures, kinetic energy of the molecules will increase, due to which the collision between the reactant molecules will also increase, due to which the rate of the reaction will increase. Okay. And third way is the pressure. So let's say if we also increase the pressure, the contact between the reactants will increase, due to which the rate of the reaction will increase. Okay. And catalytic activity, same. If we are having the higher reactant molecules, which will react with the catalyst, due to which our rate of the reaction will increase. And let's say if we are using in catalytic activity, if we are using catalyst, right, heterogeneous catalysis, so by using the heterogeneous catalyst, which will help us to lower the activation energy, okay, without utilization of the catalyst, right? So catalysts are the inert catalysts are inert, right? So which will so for the particular for the reactions, if we are using the catalyst, which will help us to lower the activation energy, okay, and due to which the rate of the reaction will increase. Okay, rate of the reaction will increase. So all these, the concentration of species, temperature, pressure, catalytic activity, comes under the intrinsic factor. So we are understanding, analyzing at the molecular or kinetic level. Okay. So for the temperature, we'll also understand the Arrhenius law, right? The dependency of the rate of the reaction with respect to the temperature. Okay. Now we are coming to the extrinsic or transport properties, right? Transport factors. So in extrinsic and transport factors, we have the diffusion and transport rates. So let's say, which means how the reactant molecules will reach to the reaction site present in the catalyst. Okay, it's called the extrinsic or transport factors, okay, in which we have the diffusion and transport rates. Okay, so we'll understand all these fundamental terms in very detail, right, in the further upcoming lectures. Okay, so I hope this is clear, right? So in microscopic reactor performance, we have the rate of the reaction. The rate of the reaction is the function of concentration of species, temperature, pressure, catalyst activity, and diffusion or the transport rates. So as we are comparing, so microscopic reactor performance, we are comparing with the macroscopic reactor performance. The microscopic reactor performance was the behavior inside the reactor volume. Okay, here is the microscopic reactor performance. Now we are understanding the macroscopic reactor performance, which means at the reactor boundaries. So this is the reactor boundary. Black line indicates the reactor boundary, right? So macroscopic reactor performance, in which we will understand the overall reactor behavior. Okay, in macroscopic reactor performance, at which we'll understand the overall behavior of the reactor system at the reactor boundaries, right? At the reactor boundaries. Okay, so by understanding the overall reactor behavior, which means what we measure at the reactor boundaries, Okay, what we measure at the reactor boundaries. So let's say we can measure the inlet and outlet molar flow rates, right? The inlet and outlet molar flow rates, which indicates inlet molar flow rate is indicated by Fa naught and outlet molar flow rate is indicated by Fa, right? So inlet molar flow rates of the reactants which we feed in to the reactor system, and the exiting molar flow rate as a product, right, which is exiting to the reactor system. Okay, second, we can also understand the overall conversion. Okay, third, the total generation of species. Let's say after the completion of the reaction, what is the total number of moles of product which has been generated after the completion of the reaction, right? Followed by reactor volume, yield, selectivity. Okay, so let's say by understanding the general mole balance equation, by understanding the microscopic reactor performance and the microscopic reactor performance, and in the microscopic reactor performance, we can also understand like what specific volume of reactor we will be requiring to achieve the desired conversion, selectivity, and yield of the desired product. Okay, we can understand by the microscopic reactor performance. Okay, and economically feasible. For let's say as a chemical engineer, we need to also understand, let's say if we are scaling up the lab scale data to the industrial scale, then whether to design a reactor is feasible or not. We can compare, we can understand by the by accounting the economics, right? So we have third, in which we have versatility, right? Versatility, which means one equation is applicable to many reactors, right? So let's say general mole balance equation is universal, which can be applied to any reactor system, any reactors, whether we have batch reactors, whether we have continuous starting reactor, whether we have plug flow reactor, whether we have packed bed reactor, fluidized bed reactor, semi-batch reactors, or bioreactors, right? We can apply the general mole balance equation to each and every reactors, which is the general mole balance equation is universal. Now let's say fourth is the importance of general mole balance equation in the core chemical engineering. So the general mole balance equation is the backbone of to design any reactor system, right? Okay, so in order to design a reactor system, we will understand the general mole balance equation. So in CRE1 and CRE2, we'll learn to design reactor system. In order to design a process, let's say if we want to establish a plant or in industry, right, then as a chemical engineer, we need to understand, we need to analyze, like for the reaction, what type of reactor I will be requiring for to take the reactions, right, to run the reactions, right? Second is what size of reactor I will be requiring. Third, if let's say for what size or volume of the reactor I will be requiring to achieve the desired conversion, selectivity, yield of the desired products, right? And what are the operating conditions the reactor will be operated. Okay, so all the questions we can understand and by understanding the general mole balance equation. Okay, so let's say by using the advanced softwares like SPEN Plus, SPEN HiSys, COMSOL, GPROMs, we can understand, we can model and simulate entire chemical reactor. We can design the reactor, we can design the process by modeling and simulations by utilizing the advanced softwares as SPEN Plus, COMSOL, and GPROMs, right? Now scale up. Let's say if we have the lab scale data of kinetics and rate laws, right, then by plugging those lab scale data into the general mole balance equation, we can scale up to the industrial scale reactor systems, right? Fifth point is the practical applications of the general mole balance equations. So what are the applications of general mole balance equations, right? So general mole balance equations will be applied to each and every in the chemical industries, right? Each and every industries will be utilizing the fundamental concept of general mole balance equations. So let's say we have the example, let's say the petroleum refining, the pharmaceuticals and fine chemicals, polymer industries, environmental engineering and sustainability applications, the energy sectors, right, for fuel cell and batteries, fertilizers and agrochemicals, food and processing industries, materials and specialty chemicals, green energy and future technologies. And each and every industries will utilize the concept of general mole balance equations. Right? So general mole balance equation can be formulated as in minus out plus generation is equal to accumulation. Right? So in the further lectures, we will delve more deeper into the fundamental concepts of general mole balance equations. Okay, how we will derive the general mole balance equations for the different types of reactor. For each and every reactor, we'll try to derive the design equation by utilizing the concept of general mole balance equations. Okay, so I request you to please make a note and please try to please understand all the things. Okay, and please if you have any questions, then feel free to comment below. Okay, I will try my best to reply to your every comments. Okay, so in today's lecture we understand, so in order to conclude in today's lecture, we understand the key fundamental concept of chemical reaction engineering, which is the general mole balance equation. Right, we understand the we understand what are the intrinsic factors and the extrinsic factors or the transfer factors. Okay, we also understand the comparison between the microscopic reactor performance and the macroscopic reactor performance, followed by understanding of the versatility of the general mole balance equation, which is universal and can be applied to any types of reactors, followed by the applications of general mole balance equations. Right, and in further lectures we will delve more deeper into the fundamental knowledge of the general mole balance equations, where we will derive the general mole balance by utilizing the general mole balance equation. We will design the equation for each and every different types of reactors. Right, so I request you to please make a note, and if you have any questions, feel free to comment below. I will try my best to reply to each and every comments. Okay, so until then, stay focused, keep learning and stay curious. Okay, so thank you for watching my video. GMBE.